Thank you very much for the invitation. It's great to be back after 4 years to this seminar, and you guys are doing a fantastic job to keep it running. So nice to be back. So coincidentally, something that I've been talking about today is related to what I've talked about 4 years ago, at least in terms of flavors. And well, I won't assume that you are familiar with my talk 4 years ago, but so what I want to talk about today is extremal problems about the character sum. So I'll begin by telling you what are those two problems that I would care about, and I want to take a somewhat different approach to these distributional questions that usually been taken. And then I go ahead and tell you why other people from other parts of mathematics, say in analysis or computer science or well, number theory as well, care about related things and how to actually attack those problems using machinery or using this distribution of the character sums. So the main thing is today is to change somewhat the perspective on this distributional questions. And let me go ahead and tell you, roughly speaking, what I'm talking about. So I'll talk about, I'll fix a heuristic character, let's say primitive character, and whatever I will restrict myself today to the prime moduli, Q. And what I'll be interested in is the exponential sum, exponential sum of this type with the character coefficients. So I specifically do not normalize this at the beginning here, because normalization is a tricky business and it will depend on ranges. But roughly speaking, what I care about is the following. So the first question is that, so what is the distributions if I take various ranges of x and q, and I look at these character sums? So I fix my theta in the exponential sum, and I look at how do these partial sums behave when I average over all characters mod q, and I let q to go to infinity and x to go to infinity. Again, I do not care about the normalizing factor at the beginning. So the key thing, what I care about is that the angle theta is fixed. So you can think of n times root 2, for instance, as being the angle. I will mostly care about the rational ones, but rationals also make sense. And the second question that I care about, also very natural one, is that now suppose I fix the character, let's say quadratic character, Legendre symbol, and now I care about what is the limit in distribution of this exponential sum when I sample theta uniformly and random on the unit circle. So roughly speaking, these are the two quite classical questions, and there has been a lot of work on the related kind of questions. Let me just mention a couple of them. And by the way, I do apologize if I forget like some names. There are a lot of names in this talk from different side of mathematics. So if I forgot someone, this is not on purpose. So if theta equals to 0, this is just a partial sum of the characters. And the distributional aspect of that have been studied, in particular, the maximum of character sums, starting from the pioneering works of Montgomery Vaughan, and Bober, Goldmacher, Granville, Dimitris, Granville Sound, Lamzuri. So many people studied the distribution of the maximum of character sums, and that is by now quite well understood, at least in some way. So whenever theta equals to 0, the other distributional aspect that someone said in chat that there is no voice. Can you hear me?
I can hear you fine.
Okay. Well, I can speak louder, but I don't think it will help. Okay. So another aspect that has been studied by people is that for theta equals to 0, and if I look at this function as a function of the length, t times q, so I look at it as a function of t, and then the distribution as a function of the length has been studied quite a bit by Ayesha Hussein, who was in Bristol here, and then Hussein and Lamzouri for quadratic characters in the families, and for cubic characters like now Yunus and Nath. So many works in the in this aspect of work. So why I said that the normalizing factor is interesting here, that the result of Harper, like a well-known result of Harper, tells us that actually, typically, whatever it means right now, on average, the character sums, as long as the length satisfies these restrictions, it's actually little o of square root of x. So square root of x perhaps is not a natural normalization if your length actually either goes to infinity, or it goes to infinity, and q over x also goes to infinity. So distribution in this range is not understood, and this is a very interesting, obviously, question. But for theta not equals to 0, this is a much less studied question. So one recent work on that was by Wang and Xu. It's a very nice paper where they actually considered irrational theta. And what they proved is that if you take a smooth version of the sum, then the characters, the exponential sums for fixed theta, behave like square root of x in size. So in this case, perhaps it is natural to normalize in this way. And also very recent paper of Del and Milecevic, Georgia, again, theta now is 1 over q, so this looks like a Gauss sum. And again, the aspect of the distribution is in terms of the length. So you look at this as a function of t, and you look at the distribution as a function of length. This is not the aspect that I want to consider in this talk. But I also mentioned here the work of Montgomery, actually, and our work with Lamzouri and Mark. You've heard some talks of Lamzouri and Munch in this seminar about that. So where we studied the LP norms of Facetta polynomials, a famous paper of Montgomery on the infinity norms of Facetta polynomials. So this is in some sense a distributional question about the LP norms. I'll talk about that more. So this is roughly what I'm interested in this type of questions in this talk. So why other people would care about these things? Number theorists, of course, do, but why other people care? So other people in analysis and computer science care because of two things. So there are two famous classes of polynomials. So one of them is Facetta polynomial, where I just stick the character in my coefficient. And this has been known for about 150 years, for about 120 years, 100 years. So, of course, if you evaluate this polynomial on the unit circle, then you get an exponential sum with the character. And so different aspects of this polynomials have been studied. It's a famous object. And Turyn polynomials is less known to number theorists, but it comes from the 1960s work on the Golay problem or merit factor. So what is this polynomial? This looks like a Facetta polynomial, but now what I do is that I change my length, and I also allow to shift my character by beta times q. So these polynomials appear very frequently, and other people care about them because they're of extremal problems for Littlewood polynomials. So I will get back to that. But now what I want to tell you about is about this. What are these extremal problems of Littlewood polynomials? That is actually a very popular subject for analysts. So with many beautiful problems. So what is the setup? So the setup is simple. So what is Littlewood polynomial? Littlewood polynomial is just a polynomial with plus minus 1 coefficients. And at the end of his life, Littlewood writes about 8, I think, papers on these plus minus 1 polynomials, outlining an enormous number of problems about extremal problems about them, about the zeros of polynomials, about the LP norms that I will be talking about, which have been tremendously influential in the past 60 years. in analysis, combinatorics, number theory, and so on and so forth. So tons of interesting problem, and I want to tell you at least about a couple of them because they're perhaps a bit less familiar to the number theory crowd. So what are these extreme problems? So for q between 0 and infinity, I will define mq to be just the qth moment of the polynomial on the unit circle. And for q equals to infinity, this is just the L infinity norm, which is just the maximum on the unit circle of these polynomials. And one of the important things that I want to talk about here is the q equals to 0 case. So the q equals to 0 case for this is what is called the Mahler or exponential Mahler measure. So for analysts, this is just the LQ norms when q goes to 0. So this has this nice expression in terms of logarithmic potential. And for number theorists, if you use generally, if you use just the Jensen's formula, then you are immediately getting that this is actually a product of the Galois conjugates, or the product of the roots that are bigger than 1 of the polynomial in absolute value. So the Mahler measure, of course, I will not convince you that it is an important function for number theorists. For analysts, integrating the logarithm, it is another very important object because it captures the zeros. So this is a rather well-studied topic, and I want to talk today about these extremal problems about the Mahler measure. So what Littlewood asked about these gadgets. So Littlewood asked about what is the minimum and maximum of the norms of these Littlewood polynomials of different LQ norms. So as simple as that. For given Q, what are the extremals? Asymptotically, exact extremals, everything you can tell me about that. So he had like precise questions. I want to tell you, just now show that this is actually a very interesting question because these problems are hard. So why these problems are hard? So, So let's warm up. Some of them, if q equals to 2, then I just integrate my polynomial on the unit circle. And of course, by orthogonality of my exponentials, I just pick up my coefficient squares. And this norm is very easy. So the maximum or minimum is completely flat for every polynomial. Everything is the same. So L2 norm is very easy to understand for Littlewood polynomials. But if you take q to be infinity, then of course, if I ask you what is the largest L infinity norm, then just by triangle inequality is smaller than n plus 1. And it's easily seen that I can take this polynomial, just the Dirichlet kernel geometric progression, and that is where the maximum is attained at z equals to 1 on the unit circle. So this is simple. The largest L infinity norm is simple. What about the smallest one? Well, clearly the L infinity norm, the maximum is always bigger than L2 norm. So L infinity norm is bigger than square root of n plus 1. And Erdős conjectured that, in fact, you cannot get arbitrarily close to square root of n. So it's a famous conjecture which is still unresolved, but it is related to another couple of famous problems. So the conjecture of Erdős first, and actually it attributes it to Littlewood, that at the same time, I guess Erdős changed his mind, but at the same time, Littlewood famously conjectured that ultra-flat polynomials exist. So what is this? This means that I give you epsilon, and you can find a polynomial Pn for given epsilon, such that on the unit circle, I should say that this is for every z on the unit circle, you are between 1 plus epsilon, 1 minus epsilon from the L2 norm. So this is a very well-known question about ultra-flatness, and which is still open And people believe, I guess, depends who you ask, whether they exist or not. But if you allow complex coefficients, modulus 1, this is a famous construction of Kahan, random construction that such polynomial exists, the ultra-flat one, and Bombieri-Bourgain, they've given the deterministic construction. The paper is extremely complicated to read. It's a long paper. But for complex coefficients, we know that ultra-flat polynomials exist. Okay, but if you restrict yourself not to ultra-flat polynomials, but to flat polynomials, so you allow different constants C1 and C2, and this has been solved very recently by these 5 gentlemen. So they constructed the polynomials that are allowing to have like different constants in between. So you can see that L infinity norm is already a hard question. For q equals to 1, this is also a famous result. So if you ask what is the smallest L1 norm of Littlewood polynomials, then it was also conjecture of Littlewood. Kayagin and McGee, Smith famously solved it independently in the 80s, that if you take an L1 norm of any exponential function, then it is always bigger than, well, if you think about coefficients plus minus 1, oops. So if you think about this as being plus minus 1, then it is always bigger than logarithm of n. So this is a very well-known conjecture of, was a well-known conjecture of Littlewood, and now it's a theorem. But if you ask what is the largest norm, this is actually a much less known paper of Klemish, which I knew from the banjo, and he was told by Fyodor Nazarov. It's published in a Russian journal that I was not aware of this paper before. So it's a very nice paper where Klemish proved that this Dirichlet kernel, it minimizes LQ norms for every q between 1 and 2. And it maximizes LQ norms between 2 and 4. And Littlewood conjecture that should hold beyond 4 as well, but it is still open. So at least in this case, we know the maximizers and minimizers, at least in terms of the order. So it's a very nice, nice result, which is not very well known, at least to people. Okay, so you can see that lots of open questions around these extremal problems. And one other historical bit is the q equals to 4. And q equals to 4, it's also very famous object in computer science. It is something which is called merit factor problem or Golai problem. And so L4 norm has a very nice expression. If you just open up everything and integrate, you know that L4 norm is nothing else but the second moment of the self-correlations of your function, of your polynomial. So this problem has been studied very widely. So what is the question of what is the smallest possible? The largest is clear. I can stick AM to be 1 all the time, and I'll get the large L4 norm. But what is the smallest L4 norm? So this question comes from computer science, engineering, chemistry. So people have studied it in many different fields. Because this provides, if you can construct the polynomials with a very small self-correlations of the coefficient, then you construct a very much pseudo-random, very nice sequence which has a small dependency in between yourself. And so there has been a long quest. So Golai, came in 60s, and then people have been improving. But for a long time, this minimum merit factor is, by the way, something different. It's a normalized L4 norm, but essentially it's equivalent to finding the polynomials with the smallest L4 norm. So the record here goes back in 2013. So Jadweb, Katz, and Schmidt, they showed that you can construct a polynomial. So of course, L4 norm, when you normalize it by L2 norm, I tend to normalize everything by L2 norm just to have a scale. So what, of course, L4 norm is always bigger than L2 norm by monotonicity. So the goal is to get to 1 as close as possible. And so what they did about 12 years ago, they constructed the polynomials that the L4 norm is a bit bigger than 1, but smaller than 2219. So this C is the root of this cubic equation. And well, actually, they proved the construction works. So computers, Borwein and Choi and Jedwab in 2000, they actually found numerically this polynomial. But it was proved 10 years later with number theorists. And the extremal polynomial here is the Turyn polynomial. So this is like where they appeared. This is Turyn polynomial with some parameters that I will talk about a bit later here. So it is related to this character type question that I considered before. Yeah, it's okay. I'll come back to this eventually, but let me just right now talk about actually what I want to talk about. So what I want to talk about is the case q equals to 0, and q equals to 0. This is the what is called Mahler problem. I call it Borwein-Mahler problem because Borwein popularized it. So the question is very simple. So it's a question from 1963 by Mahler, and so I give you the Mahler measure. I will normalize Mahler measure, and my question I normalize by L2, and my question is, what is the smallest? What is the largest possible Mahler measure of Littlewood polynomial? So if ultra-flat polynomials existed, then I could take this ultra-flat polynomial and I would just know that this constant, this lim sup, is equal to 1. Again, it's always smaller than 1. I should notice that this ratio is always smaller than 1 because L0 norm is smaller than L2 norm. But whether you can get arbitrarily close to 1, it's not clear. And the Mahler asked, like, can you construct large Mahler measure? So it's interesting that in this norm, there is a famous question of Lehmer, the opposite question: what is the smallest possible Mahler measure for all integers, and in particular for Littlewood polynomials? And this is a famous Lehmer question from 30s, where the conjecture is that I cannot, of course, Mahler measure is always bigger than 1 because it's a maximum of the roots, but whether you can get arbitrarily close to 1 is an open question. And as far as I know, nothing has been improved since the very well-known result of Dobrovolsky. I might have confused the exponents here, though. But Dobrovolsky proved that instead of getting a uniform epsilon here, we can actually get something which goes slowly to 0. But whether this is the truth or not, nobody knows. So it's a very, you can see that in L0 norm is sort of one norm where Mahler measure, where both the upper bound is the well-known open question and the lower bound is also well-known open questions. So we don't really know. Okay, so I want to talk, I will not tell you anything about Lehmer conjecture, but I will tell you something perhaps somewhat new about the Mahler problem. And so previous works on that, I listed with some people, perhaps not I mean, certainly not all of them, but basically those are people that proved some estimates for the Mahler measure of some certain families of polynomials, and they give you some constant in this MBs, like lower bounds on MBs. So we started from Littlewood, and the record previous is okay. So let me just say one thing, that if we so it started from Littlewood, but Fielding and was the first to actually solve the Mahler problem for complex polynomials. So before the work, so if you restrict yourself to the complex coefficient A1, then it was proved in the 70s that MB is actually, you can get arbitrarily close to 1. And Ballard and Newman after that proved like more quantitative results. But of course, it follows from Kahan and Bombier and Bourgain because we know that ultra-flat polynomials exist. So you can just plug them in there and you will get a large constant. But these results of Field and Ballard and Newman, they're much more, I mean, also probabilistic, but they have been proved before and they are easier to prove actually than the flatness question. So then lots of people have had like different input here. The previous, I will not tell you the numerical things. I will say that Michael Mosengo, based on our work with Eunice and Mark, had a record before. So I want to tell you about a theorem, finally, one theorem. So this is a joint work with Bristol's theorem. So with Jonathan Bobber, who's my colleague here, and our student Besford Shala. So what we proved as the corollary of this Mahler business is that you can get that MB is actually bigger than 0.954. And the construction is, oh, these are wrong numbers, actually, now. I see that they are wrong, but the construction is that to get a very large Mahler measure, what you want to do is you want to take a Turyn polynomial, and you want to take a particular shifts with this alpha length slightly bigger than p, 10% bigger, 14, and beta being a shift which is roughly 1/3. But it's actually not. Okay, don't believe me in these constants. They're changed since then. But this quantitative guy did it. So what is interesting here? So the interesting thing that you can get extremely high constant, which is by using deterministic, completely deterministic construction. And so what we know in this we know only one polynomial, which is I learned from Michael Mosengo, of degree 12, which gives, it's a fixed polynomial of degree 12, like similar story happened with Lamer problem, which gives you the constant 0.98. So we don't know the family, but if you ask for one polynomial with the large ratio of L0 and L2 norm, there is one which is 0.98. And we don't know anything in between. But you can get as large as this. This breaks this record, what we knew at the 0.95. Okay, I'll tell you one more application here, and this is related to these merit factors and Turyn polynomials. So there is a conjecture related to this merit factor of Günther and Schmidt, that if you take Turyn polynomial of the full length and you look at the shifts, then actually the flattest polynomial that you can get is for the shift alpha equals a quarter. So what I mean by that is that if I give you any integer k and I look at the normalized L2k norms, so 2kth moment, then what they conjectured is that for every k, the least possible ratio is achieved when the shift is 1/4. They proved this conjecture before for k equals to 2 and 3, using like by hands manipulations with characters, but it was open for higher k. And the interesting bit here is that for a very long time, merit factor was believed to be delivered. The best merit factor was believed to be delivered exactly by this polynomial. And the reason being that they're kind of the flattest out of all Turyn polynomials of length q, exact q. So it was until Borwein and Choi and Jadwab found in 2000 this numerically new polynomial, Golai and I think other people in working in merit business, they actually conjecture that perhaps that might be the one which delivers the extremality. So basically, these are believed to be the flattest ones, and as a byproduct of what I've been talking about characters, so this conjecture, so it's also our theorem that the conjecture is true. It's indeed the flattest in this family of polynomials. And also another interesting byproduct is that you can recover all these previous results on Turyn polynomials vector from as a general, just from our results, general results. So this best result on the merit factor of GenVep and co-authors that I mentioned would be a consequence of that too. Okay, so I guess I am finally ready to switch the gears and tell you, once I told you these applications, I will actually switch the gears and go back to characters. That's more. No, I will not. Okay, so one more word about the, if I want to attack the Mahler problem, one thing to ask immediately is the question, what happens for random Littlewood polynomial? And I will give you this result because it illustrates one of the difficulties that we have to overcome, very important one. So what happens for random polynomial? The story here is interesting. So I will remind you that the Mahler measure is just this integral of log. And this is the result of Choi and Erdely, that the average Mahler measure of the Littlewood polynomials, so I take all of them, there is 2 to the n of them, and I look at the average value, and that has happened to be 0.749. And the key input in the proof of this, so I should start, there are 2 key inputs here. So one is, this is very old result of very classical of Salem and Zygmunt. So if I give you random coefficient plus minus ones here, then if I ask where does this exponential sum converge when I normalize appropriately, then this is going to converge to the central, by the central limit theorem, to the Gaussian, complex Gaussian random variable. So I average over theta, and I also average over AK. So this constant e to the minus gamma over 2 is nothing else but integral of the average value when you integrate against the Gaussian distribution. Logarithm, when you integrate the logarithm against the Gaussian distribution. Because we believe that the polynomials, the behavior on the unit circle is Gaussian. So the key here is that, and this is what is very important to know about these problems about the Mahler measure, is that the second key input, and this was really Choi and Erdely proved it shortly after Kanyagin and Schlack proved this, their result. So whenever you want to prove something about log on average, so you need to understand not only the large values and typical values of P, but you need to understand, because integrating log is hard when P is very small and close to 0. So what is a deep result of Kanyagin and Schlack says is that the time that your random polynomial spends around 0 is actually small. So this is what is called in analysis small ball probability, and this is what is an important ingredient in all these proofs. So you need to show that logarithm doesn't live a long time around 0. So if you combine these 2 things and do some work, you will get your Gaussian behavior. Okay, so back to character sums. So in the last like 15 minutes or so, I want to tell you actually something about the character sums. So what is this new take on the character sums that I want to take? So let me consider, I want to understand the distribution of character sum, and let me write it down. So let me fix the length. I will consider the lengths between alpha q and alpha plus beta q, where alpha and beta are fixed numbers. And just for convenience, I will normalize this by some factor, which depends on k. And what is k? So I will write my theta as the k over q plus t over q, where t is between 0 and 1. So rational approximation. So the way to think about these character sums in distributional terms, what I want to do is I want to think about that as the following question. So I want to partition my circle. So this is like a character sum of length q. So what I want to do is I want to partition it in q intervals, and I want to ask the following two questions. So the first question I want to ask is, if I fix my character chi, so let's say this is a unit, Legendre symbol. I want to ask, like, if I choose k randomly, if I choose this piece randomly, what is the distribution? How does it behave? So it's a different question than what I asked before. But if I ask this question, so what does the typical piece look like when I choose it uniformly at random? And the question two that I want to ask is related to the previous question. So now I want to fix k, let's say k equals to 10, and I want to look at the piece between 10 on q and say 11 on q. And I want to ask the question, if I look at the randomly chosen character, not the fixed character, what is the distribution of the random piece? And this is the theorems that I want to state you right now about what I want to tell you about. So to answer these questions, so this is this new take on the character sum distribution, that I want to look at the distribution of the local piece instead of looking at the entire distribution. So to answer these questions, I need to introduce several objects right now. So the first object that I want to introduce is this not particularly nicely looking expression. So the expression is the following. So I look at this function t between 0 and 1, this random series. So where the coefficient yl, those are independent random variables distributed plus minus 1 with probability half. And then there is this normalizing factor that you shouldn't worry about. And then there is this exponential sums that for now you shouldn't worry about too much. So alpha and beta, these are my lengths, and I'm summing over all else. So this becomes like a random Fourier-like series. So the theorem that I want to say is that if for each fixed alpha and beta, the first theorems, if you look at this as a random process, and I set here J, so this is for the case where I fix character. So remember, I fix character n on q, Legendre symbol, and I choose randomly k between 0 and q minus 1. And to this random, so I look at this as a random process. So what I do is that for every k, I have a randomly chosen, I have a function of this type. So it's a random process for the fq, for the first q integers, into the space of continuous functions. This is as a function of t. So the theorem is that if you look at this sequence of random processes, when you choose k randomly for the fixed character, it converges to this limiting object, which looks like a random series. So just that is, bear with me. And this answers sort of a second question of when the character is fixed. But what to do when the character is not fixed? So what I want to answer now is that what happens when I take a fixed sequence of k, which might depend on Q. And when I average over, when I take a random character. So I need to introduce something different. So I need to introduce two random processes here. So one of them is the random process where, again, so this is X is the uniform on the unit circle. So now I don't have quadratic characters. I only have characters which are complex valued. So X is uniform on the unit circle. W of K minus L. So remember, K is fixed. So W of K minus L. So W here is the random multiplicative Steinhaus function. So it's just a function which on primes is the uniform and independent for different primes. And then you form a multiplicative function. So I take this random multiplicative function and I shift it by K. I can define it on negative integers as well. And again, that there is this exponential sum weighted by some coefficient, which becomes like a random series. And omega of n and x are independent random variables. So I will also need to define the modification of this process, where now I also look at some normalizing factor, something which you had before, but now the coefficients are just uniform IID non-multiplicative. So important thing here, they are non-multiplicative. So that, again, two objects, the key thing, random multiplicative times something not particularly nice, and non-multiplicative something. So here is the theorem, and bear with me, I will try to go through that right now a little bit slowly. So dependent, remember one more time, so K is now fixed and chi is random. So there are, depending on how fast K grow, we have a different behavior of this limiting processes. So if K is fixed, K is say 100, then the claim is that if I look at the random process where I select K, where K is fixed, but I select character randomly, and I look where these guys converge, that they converge to the random process with multiplicative on W. So multiplicativity is important when I could go to infinity along all primes. So I know my limit, and that looks like something. So the second thing is that if K is not fixed, but K start growing to infinity, but K is still Q to the little o to 1, then I still have the convergence, exactly the same convergence, but now multiplicativity is not important. So the effect of multiplicativity vanishes as soon as you start growing, and you converge to the process without multiplicativity. So now this is noticed here, I have a convergence along the all primes that are all set of primes. But once KQ are growing and KQ start growing quite a bit with Q, so pi of Q is the number of primes, then there exists a full density subset of P of primes, such that the convergence of these processes are only along this full set density primes. So you have to exclude zero density subset of primes where the convergence start behaving in a weird way. But apart from that, there is a density one set, and this is a necessary condition. And finally, there is an interesting regime here. So if theta is irrational number, I will explain why I'm interested in that. But if theta is any fixed irrational number, and I look at k of the order integer powers of k times theta, then if I ask myself, where do these guys converge for this specific sequence of k's, then the theorem is that, again, there is a full density subset such that the random process, which I described before, converges to something where multiplicativity is not important. So the key takeaway, multiplicativity is only important where k is bounded, and after that it is not. So this is not that easy to parse if you're not familiar with these things or didn't care about that. So one simple corollary to feel what we're talking about is it was actually a question of Victor Wong and Xu. That was the starting point of our work, is that if you take any irrational theta, then there exists a full density subset of primes such that if I look at the q's in this set, such that the fractional parts converge to some value t naught, then as a random variable, these character sums converge to this explicit random variable that I mentioned before. So this is true for every fixed theta, and this is kind of important. So this gives you just no random process. This is just a convergence of random variable where I fix theta and select chi uniformly at random. Okay, so I have a couple of more minutes. I will obviously not be able to tell you anything comprehensive about the proof in this couple of minutes. I will just tell you why. Maybe I will not tell you why these things are related to the problems that I was talking about, but or perhaps I will. So the reason why these things are important for these extremal problems is that this convergence of the processes. So how do you apply these convergence result of characters? So the way you apply it is that if I want to find an integral and I have any polynomial on the unit circle, then what I can do is I can split. So think of that. If I want to compute the Mahler measure, this is log. If you want to compute LP norms, this is something L to the 4 or something like that. But if you want to compute this integral, anything distributional, you can split your integral into pieces of lengths 1 on p and do simple linear change of variables. And now what you're doing, you're averaging over exactly the gadgets that pop up in my distributional question. So to study this distributional question, I can regard this as a discrete random process on FP. So if I establish the convergence of random processes, I can just very simply, well, not simply as it turns out, but I can just deduce the convergence of these guys. Okay, so I will not have much time to tell you about the proof. I will only tell you a very 3 words about this. So the ingredients in the proof is that the Poisson summation formula allows you to see where the randomness is coming from, and to prove convergence of random processes, you need to use something which is called Prohorov's theorem. So this is a computation of the moments and tightness. So the randomness of the characters, like how to compare to some random objects, comes from the Deline's bound or Veli's bound, but strictly speaking, you need Deline's bound because they are weighted by the characters. So the randomness comes from the Veli's bound and Deline's bound. So one important thing that here is kind of new is the fact that integrating log is hard. And I will spend like 2 minutes just telling you about this. So the 2 minutes, in 2 minutes, once you want to integrate the logarithm and find the Mahler measure, this functional, which you have, which you want to plug in, this is not a continuous functional on the space of continuous function. So taking integral of log is not a continuous functional. So the integrated log doesn't follow from convergence of the processes. And this is the usual problem in the study of, in analysis of what is called log integrability, small probability, small ball probability, and so on and so forth. So there is an enormous number of problems in analysis of how to integrate, where you need to integrate the logarithms. So the main problem that this is not continuous functional, and you need to deal with that. And I would love to explain to you why you need to restrict to the density 1 subset in these theorems that we had. So perhaps, yeah, let me just say, because this is neat. And so how do we deal with the, in 2 words, with the integrability of log? So in 2 words, this is actually a quite general way. So in order to integrate the logs, because logs can be small, you take, if you pick your favorite epsilon, and if you need to integrate log, then on the set where your function is bigger than epsilon, integral of log restricted to that set is a continuous functional. So you can apply your convergence. Well, if you smooth it. But what you need to understand in all these problems is basically this quantity where you integrate your log of these realizations, and you want to integrate it on the set where you're smaller than epsilon. And the problem in our case, this is again the usual problem, you saw it in the random case, but the problem is that if you look carefully at our expressions for the limiting guys, they are not absolutely convergent. And to check numerically something, if you want to control your guys here, so the usual way to do that is to somehow try to control derivative. To say that derivative doesn't spend, is bounded away from 0, and then you escape the neighborhoods of 0 quite fast. But because our series do not converge absolutely, this is actually not feasible. And so the nice idea is the following. I will state it and I will finish. I will state this proposition. So the nice and soft idea, which is actually applicable in other situations as well, is the following. So suppose I give you a linear differential operator with constant coefficients. And suppose I manage to prove that my linear differential operator for every t is between 0 and 1 is bigger than 1 or separated from 0. Then I claim that you can integrate log, namely that no matter which function you take, which satisfy these properties, if you restrict to the set smaller than epsilon, then your logarithms can be controlled. So this is a very soft theorem, but it allows us not work with one particular realizations of our processes, but it allows us to cook up a linear differential operator where your now series are absolutely convergent. And then we can use numerical verification to split the interval into 5,000 intervals. And on each of these 5,000 intervals, use this type of integrability. So this is one of the important ingredients. And I guess I'll stop here. I will not tell you about 2 other things, but I guess I don't anymore have time, right?
Maybe 2 or 3 more minutes.
2 or 3 more minutes. Then I can tell you. So this is like how we deal with the log integrability, and this happened to be like quite general and useful for other purposes. One thing that I wanted to explain to you why I have restrictions to density 1 subsets. So what happens when you compare the random model and deterministic one? What happens is that you end up computing what you need. You end up computing moments of the character sums, which I haven't written yet. But you end up, like for your given k, you end up looking when the moments, the contribution comes from the terms which governed by the solutions to this polynomial congruences. So I take my favorite integers m1, m2, ml, and n1, n2, and ns, and the contributions come from those terms where kq solves the equation mod q for up to truncations for some small coefficients. And so what happens is that generically, so what you need to do is you need to, if you have for some polynomial of small height, if kq happen to be a solution of non-trivial, non-diagonal solution of this polynomial congruence, you get a contribution to the moment. And this contribution to the moment skews the distribution. But generically, what you can do is that you can count the number of these solutions for how many primes kq solves this polynomial congruence, and you can count them and show that for polynomials of small degree, it doesn't happen too often. So you can remove these bad primes where these coincidences happen on non-diagonal terms. And that allows you to pass to the density 1 subset. So I guess I will just add one more word, and I should have started with that, where the randomness comes from. The randomness comes from Poisson summation formula, and this is the expression where the character sum, I don't know why I put it at the end, but this is the expression which governs this. We can stare at it. So I will finish here and we can stare at it for a minute. Thank you very much.